Hello everyone, and thanks for watching Edupedia World Videos. In this video, we'll learn the rotational analog of force, which is called torque. Right? So first, let's look at a standard example which we see every day. Let's say this is a door hinge, and this is a door which is attached to that hinge. Right? So now I have to open or close this door. We know that the handle is generally kept at the end. And you can do this example at home. If you try to close or open the door, but you don't apply the force at the end, you apply the force at the middle, you need to apply a much greater force to open or close the door. If you apply a force right near the hinge, you would not be able to open or close the door because the force required would actually be greater than what you can apply. But if you apply the force at the end, then a reasonably small amount of force can actually open or close the door, right? So this is because the force is not the only thing that is taken into account when moving the door. Where you apply the force is also important, right? That is something which we've not seen before because we were only looking at particles. If you're looking at a particle and I say a force is applied upwards, then the force is applied like this. It doesn't matter where the force is applied, right? But if I take an extended rod and I say a force is applied upwards, it makes a difference if the force is applied in this point or at this point or in this point, right? So for extended bodies, not only is the force important, but where you apply the force is important as well, right? So we see that the smaller the distance, the greater the force that needs to be applied. The greater the distance, the smaller the force that needs to be applied. So a reasonable formula for torque seems to be torque is denoted by tau, right? There's a Greek alphabet, and it seems to be r times f, right? R is the distance from the axis. So if you have applied the force at a large distance from the axis, a small amount of force will give the same torque as if you apply a large amount of force very near to the axis, right? So we can say the greater the torque, the easier it is to move an object, right? So if you apply a small amount of torque, that is either a small amount of force or a large amount of force but very near to the axis, it will be hard to move it. But if you apply a large amount of torque, that is either a very large amount of force or a reasonable force but at a large distance from the axis, then we can get the same amount of torque, right? The actual definition of torque in terms of vectors is r cross f, right? So in this case, r and f were perpendicular to each other, so it boiled down to r cross f. But generally, this is the definition. So r is in this direction, f is in this direction going inside the plane, so r cross f is in the upward direction, right? And this is something which we'll see again and again in rotation, that the direction corresponds to, we don't say it the direction of rotation, we call it the sense of rotation, right? So if an object is rotating like this, then by the right hand rule, if I curl my fingers around the object, my thumb will be pointing upwards, right? So this rotation corresponds to this direction and this rotation corresponds to the downward direction. So anytime an object is rotating in this way, in this sense we call it, and this would be, if we look at it from the top, this would be the anti-clockwise sense and this would be the clockwise sense. So if it's moving in the anti-clockwise sense, we say that omega points upwards, alpha points upwards. Remember, all these are vectors. Torque points upwards, right? So the direction of rotation is basically given by the right hand rule, and it is perpendicular to the plane of the rotation. Every plane of the rotation has two directions perpendicular to it, and they both correspond to either clockwise rotation or anti-clockwise rotation based on the right hand rule. Okay, so this is the definition of the torque, and we see that it does seem to make sense because the distance from the axis is also important. Actually, the torque is a specific example of a very general concept which I want to discuss now, that is called the moment of a vector, because we'll see this again and again. Moment of a vector. The moment of a vector is always taken about a point. And its definition is simply r cross v, where v is the vector. This doesn't stand for velocity, this stands for an abstract vector. Actually, it'd be better if I use an abstract name, so I'll just call it the vector A. right? So these are my three coordinate axes, right? X, Y, and Z. This is a point. Sorry, this is a vector. Let's say a vector A. So we take its starting point and we take the position vector of that R, and we define the moment of the vector as r cross a. So we see that the moment of a vector does not only depend on the vector but on our choice of coordinates as well. The vector itself is independent of our choice of coordinates, but the moment of a vector is always defined about a point. So it depends on the choice of coordinates. The moment of a vector can also be defined about a line. The moment of a vector about a line is just the moment of the vector about that point and its component taken parallel to that line. So for example, we wanted to find the moment of this vector about this point but in the y-axis. Remember, when we're talking about rotation, we're talking about axis, right? So in the y-axis. So in that case, we'll just take the component of r cross a in the y direction, right? So you can take the moment of a vector about a point, it's simply r cross the vector. You can take the moment of a vector about a line. In that case, all you need to take is the component of the moment of that vector about that point parallel to the line. In this case, this was r and inside was f, to torque was pointing upwards, right? But if we took r to be something like this, in that case, this would be the direction of torque. But if you wanted to find the torque about this axis, we would just take the component, and you can find that this and this angles will actually cancel and we'll get the exact same result, right? The reason I've told you this concept is because we'll see this again and again and again. We'll later look at a concept called angular momentum, which will be the rotational analog of linear momentum. And just like torque is the moment of force, angular momentum will be the moment of momentum, right, about a point or about a line. So torque is nothing but the moment of force about a line. About a line. The line is the axis of rotation, right? So now let's dig a little bit deeper and see why the concept of moment of inertia was so important. So I'm going to look at a discrete system of particles, but the generalization to a continuous system of particles will be easy enough, right? So let's take a discrete system of particles and let's say I'm moving them all about this axis, right? So the net torque will be, I'm not going to write the vectors for now because all the vectors are in the upward direction, right? So all the vectors of torque are in the upward direction. So net torque will be r times f, and we'll add them up. We'll add r multiplied by f for each, right? Let's assume for now that the force is perpendicular to the plane of the screen, right? So we can write it as summation r times f can be written as ma. I'm just going to write I in front of all of them to denote that it's for a single particle, right? But we know in rotational motion A is equal to R alpha. That means AI is equal to Ri alpha. Now this is a key point which ultimately gives us the result in all of rotational motion. This key concept, which is that even though I've written Ri, Mi, Ai and A is equal to R alpha, I've written as Ai equal to Ri alpha. I've not written alpha I. Why? Because if this system of particles is rotating as a body, then every particle has to have the same alpha, right? So alpha will be the same for all particles, omega will be the same for all particles, theta will be the same for all particles, the angular displacement in a rotational motion, right? So we can take it out as a common. It will not be dependent on I, right? And that is the result which will help us in deriving a lot of important formulas. So I can write it as summation Ri Mi Ri squared alpha, actually, because Ri can bring out here, and alpha can be taken out as common, so it can be written as summation Mi Ri squared times alpha. That gives me equal to I alpha. You can try to do it with vectors. I is a scalar, so ultimately the result you'll see is torque is equal to I alpha, and this is the analog of F is equal to Ma, which is what we saw in linear motion. So we've seen moment of inertia in detail in the previous lectures, but I did not tell you where the formula summation mi ri square came from. I tried to describe to you why ri would be important. For example, we saw that if the particle moves with the same angular acceleration in a circle of greater radius, a greater force will have to be applied on it, right? So this is the formula, torque is equal to I alpha, which is used in all of rotational motion. Again, F is equal to ma is a formula which is independent of our choice of axis, right? But torque depends on the axis of rotation, alpha depends on the axis of rotation, I depends on the axis of rotation, right? If we want the same alpha for different objects which have a different moment of inertia, we would have to apply different amounts of torque. Not necessarily different amounts of force. We can apply the same amount of force but at different distances to get different amounts of torque as well, right? So this is the main formula, torque is equal to I alpha, which helps us determine a lot of results, right? Before applying this formula for problems, let's look at what would happen if we tried to solve it in a non-inertial frame of reference, right? So in a non-inertial frame of reference, let's say a frame which is moving with an acceleration a frame. In that case, to be able to use Newton laws, I'd just put a pseudo force of MAF, where this AF is opposite to this, on every individual particle, right? MIAFI if I wanted to write. So in that case, the pseudo torque will be the torque of this pseudo force. Okay, when we were calculating linear motion in a non-inertial frame, we took all the forces, we solved it as it was, except we just applied an extra pseudo force to give us the correct results, right? So when we are applying torque is equal to I alpha in a non-inertial frame of reference, we'll simply add up all the torques and use it as normal, except we'll add a pseudo torque which will be the torque of the pseudo force. Right, so it's as simple as that. But in one special case, it gives us a very nice result. So pseudo torque will be summation mi af, right? But af can be written as ri alpha. Sorry, this will be another ri will be added to it, right? So it gives me mi ri squared alpha. Actually, I'm sorry, this is incorrect. Right, I made a mistake here. It'll actually be MIAFRI. There will be no alpha because I was confused because I thought we were talking about rotational motion, but we are talking about pseudo force. Right? So this whole thing is happening in a frame of reference which itself is moving with an acceleration AF. Right? The acceleration of the frame. So AF will be the same for all these. Just like in the previous case, alpha was the same for every particle. AF is the same for every particle because AF doesn't even depend on the particle. Right? So in this case, we can take AF to be out common and take it outside. So we'll get summation MIRI times AF. But we know what summation MIRI is. It is M times RCM times AF, right? The position of the center of mass was basically summation MIRI by summation MI, right? We can write it as MAF RCM. So this gives us a nice result, which is that the torque of the pseudo force is equal to the pseudo force multiplied by the position vector of the center of mass. So we can assume that the pseudo force acts at the center of mass. The pseudo force does not act at any particular point. It acts on each individual particle. But if we wanted to calculate the torque of the pseudo force, we can take each individual pseudo force and we can take the torque of each individual pseudo force and add them up. Or simply we could take the total pseudo force and multiply it by the position vector of the center of mass. So this is a nice formula to calculate the pseudo torque. Right. Now another thing we can derive from this is, if we are calculating a problem in a non-inertial frame, but the axis of rotation is the center of mass, then RCM is 0 and pseudo force will have no torque, right? So the things we've learned in this particular subtopic is that pseudo force, if we wanted to take the torque of pseudo force, we can assume that the pseudo force acts at the center of mass, and hence if our axis of rotation is the center of mass, the torque of the pseudo force will be 0. And if the torque of the pseudo force is 0, then tau is equal to I alpha is valid, right? So our original statement, tau is equal to I alpha, it is always valid in inertial frames of reference, but it is also valid in non-inertial frames of reference if we calculate the motion about the center of mass. About any other point we would need the pseudo torque, But if we are calculating it about the center of mass, the torque of the pseudo force will be 0. So if we are calculating motion about the center of mass, then inertial frames and non-inertial frames are equivalent for this particular specific aspect, that is calculating, for example, alpha or I or any other quantity. Torque is equal to I alpha is valid in both inertial and non-inertial frames of reference, provided we calculate the motion about the center of mass. Right? So now we'll turn to a concept called rolling friction. Right, we've seen two specific types of friction before, static friction and kinetic friction. But there is actually a third type of friction called rolling friction, and that happens, as you can guess by the name, when an object is rolling. Right. So let's say there's an object which is moving at a speed v, but it also rolling at an angular speed omega, and this is r. Right. So the net motion of any particle, right, v, will be v of center of mass plus v with respect to center of mass. Right? V of center of mass is simply this v. V with respect to the center of mass will be the velocity of the particle if I was sitting at the center of mass. If I am at the center of mass, I would not see this horizontal motion. I would just see an object rotating itself around the center of mass. Right? So VCM can be omega, V with respect to Cm can be omega r. So let's focus on this bottommost point for a second. The net speed of the bottommost point is, it is V forward and it is omega r backwards. Right? So the net speed is actually v plus omega r when we add these two vectors. Now, if v is greater than omega r, we are talking about magnitudes right now, then the net speed of this particle is in the positive direction. Right? In that case, the friction would be acting in the backward direction. Right? However, if v is less than omega r, that means the net speed of this particle is in the backward direction relative to the ground, and obviously friction does not act relative opposite to motion, it acts opposite to relative motion. And if the relative motion of this particle is backwards, that means friction will act forwards. And this is something which we have not seen before. Friction is actually in the direction of the motion of the center of mass. Why? Because for the direction of the friction, the speed of the center does not matter, the speed of the point in contact with the ground matters. Right? So this helps us in calculating the direction of friction, and actually rolling friction is generally much smaller than static or kinetic friction. That's why it's easier to push objects when we put a wheel below them. Right? So the final topic which we'll learn is the generalization of linear momentum, which is called angular momentum. Angular momentum is the angular analog of the linear momentum, and it is simply the moment of p. P is the linear momentum, right? Angular momentum is denoted by L, and for a single particle it is r cross p, the definition of moment, and for many particles it is summation ri cross pi. Right? But let's expand this a little bit further. We can write it as summation of ri. I'm not going to use the vectors now because that makes it easier. Right? We are just looking at standard rotation, and the vectors for r will be perpendicular to the plane of the rotation. Right? So ri times pi can be written as mi vi. However, vi is equal to omega ri, and again here we see the power of rotational motion. Vi is different for each particle, the speed of each particle is different, ri is different for each particle. Right? For example, let's say we have a standard object which is moving about its center. Right? The speed of each particle is different, r of each particle from the center is different, but omega is the same for each particle. Right? So we can write it as summation mi ri squared omega, and mi ri squared can be taken out because omega is common. That gives me I omega, and now we can add the vectors like this, and this gives me the result L equals I omega, which is the analog of P equals mv. So we see that there is a clear and parallel relationship between linear and rotational motion. Right? The analog of mass was moment of inertia. The analog of force was torque. The analog of acceleration is angular acceleration. The analog of speed is angular speed. The analog of momentum is angular momentum. And just like P is equal to mv, L is equal to I omega. Right? We can see other results from this as well. What is dl by dt? It is because I will be a constant. It will be I times d omega by dt, which will be I alpha. So this gives me, which is torque. So this gives me torque is equal to dl by dt, which is the analog of force is equal to dp by dt. So now hopefully you'll be able to see that it's easier to remember these formulas if you just understand them properly and look at them as the analogs of motion as the analogs of linear motion. Right. Again, just like we have conservation of momentum, which says that when the external force applied is zero, the momentum will remain conserved. We have conservation of angular momentum, which says that if the external torque is zero, then the angular momentum is conserved. If there is no external torque acting on a system of particles, then the angular momentum will be conserved. Right? We'll see a lot of examples of these concepts. We've learned a lot of concepts right now, and we'll see a lot of examples of these concepts in the next lecture. But for example, if I have a rod and I have a point particle which comes and strikes the rod, then eventually they'll start moving in complicated directions. Right? The object might move forward or come back. The rod might start moving with some rotational speed as well. But we can take any random point and we can conserve angular momentum about this point. Just like we conserve linear momentum for collisions, we can conserve angular momentum in this sense, because when these two strike, there is an internal equal and opposite force acting, and about this point, they both will have equal and opposite torques, which will cancel. Right? Just like when we had collisions and two objects collided, they applied forces on each other, but they cancelled out, and the net force was zero. Right? So we've learned in this case that the angular momentum will be conserved because there is no external torque acting on it. Right? So I'm just going to write all of the parallels between linear and rotational motion, and we'll see examples of these and how to use them in problems in the next video. Right? So this is linear and this is rotational. We have mass and the analog is moment of inertia, which is summation of mi/r square. We have x, the analog is theta. Displacement, the analog is angular displacement. Right? We have v, the analog is omega. We have a, the analog is alpha. We have torque, the analog is f. Sorry, we have f, the analog is torque. And we have momentum and the analog is angular momentum. We have f is equal to ma. We have torque is equal to I alpha. Again, arrows over the vectors, no arrows over the scalar. We have p is equal to mv. We have L is equal to I omega. We have f is equal to dp by dt. We have tau is equal to dl by dt. We have conservation of momentum. We have conservation of angular momentum. And one more thing, we've not talked about energies yet. So let's look at kinetic energy. Right? Kinetic energy for the linear case for a discrete system of particles will be summation half mi vi squared. But for rotational motion, we can write it as summation half mi ri squared omega squared, right? Because vi is ri omega squared will come out as common. Summation mi ri squared will be I, so it will give me half I omega squared. So we see another parallel. Kinetic energy here is half mv squared. In this case, kinetic energy is half I omega squared. And you can see a lot of other parallels if you start looking at relationships between work and angular work and force and energy and stuff like that. Right. So we learned a lot of concepts in this lecture. In the next lecture, all we'll do is we'll apply the concepts learned in this and the previous lecture to a lot of standard problems which are involved in rotational motion. Thank you.